Hello my dear friends, welcome to my YouTube channel. Myself Dattu Patel, Assistant Professor from LJIT. Today's session we are going to discuss about the new topic which is improper integral type 1 and type 2. Let's see. Firstly we have to discuss about the improper integral. The integral a to b f of x dx is called an improper integral if one limit of integration or both the limit of integration are infinite, or the function f of x becomes infinite at a point within the interval or endpoints of the interval of the integration. Basically improper integral has three types. Let's see. Firstly we have to discuss the improper integral of type 1. The integral a to b f of x dx is called an improper integral of the type 1 if either lower limit or upper limit or both the limits are infinite. For example, integral minus infinite to be 1 upon x square plus 1 dx. Here lower limit which is infinite. Another example which is a to infinite 1 upon 4 plus x square dx. In this example upper limit which is infinite. In third example both the limits are infinite. These are the examples of the improper integral of type 1. Basically, we have to finding the solution of improper integral has three kinds. Firstly, if integral a to t f of x dx exists for every t greater than or equal to a, then integral a to infinite f of x dx equal to, here upper limit which is infinite, means that is replaced as any real number, that is t. Here limit t tends to infinite, a to t means infinite which is replaced as a t, and applying the limit t as a infinite, then integral a to t f of x dx, provided the limit exists as a finite number. Second case, if integral t to b f of x dx exists for every t less than or equal to b, then integral minus infinite to b f of x dx, here lower limit which is infinite means that term which is replaced as a t, and limit t tends to minus infinite, integral t to b f of x dx. Similarly, provided that limit exists as a finite number, here our improper integrals a to b f of x dx and minus infinite to b f of x dx are called convergent if the corresponding limit exists, means limit has a finite value, then it is convergent. If limit does not exist, means limit has a plus infinite or minus infinite, then it is divergent. In third case, if both the integral minus infinite to a f of x dx and a to infinite f of x dx are convergent, then we define minus infinity to infinite f of x dx equal to minus infinite to a f of x dx plus a to infinite f of x dx, where in third case the variable a which is real number, means our both the limit has a infinite, then we cannot solve it directly. For that we have to breaking the limits, and in any number we have to require, but number which is must be real value. Then here we taken the a, then minus infinite to a f of x dx plus a to infinite f of x dx. Then we have to separately check the both the integral. If both the integral are convergent, then total integral will be convergent. If either one, that is divergent, then total whole integral minus infinite to infinite f of x dx will be divergence. Let's see one example. Evaluate integral 0 to infinite 1 upon x square plus 1 dx. Here our function which is 1 upon x square plus 1, that is continuous everywhere. Here upper limit which is infinite, that means given integral is improper integral of the type 1. For that infinite which is replaced as a t and applying the limit t as a infinite, then integral 0 to t 1 upon x square plus 1 dx. You all are know about the integral of 1 upon x square plus 1, that is tan inverse x, the limit t tends to infinite, tan inverse x, where x which varies from 0 to t. Now substituting the limits, then upper limit minus lower limit, that will give you limit t tends to infinite, tan inverse t minus tan inverse 0. Then values of tan inverse 0, that is 0. Then limit t tends to infinite tan inverse t. Now applying the limit means t as a infinite. Then tan inverse infinite, that is obviously pi by 2. That is we have to find. Here our answer will be finite, means limit exists, then given integral which is convergent. Now let's see one more example. Determine whether the integral 1 to infinite 1 upon x square ds is convergent or divergent. Then find its value if it is convergent. Here 1 upon x square, that is obviously continuous function, means continuous at everyone. Here upper limit which is infinite, then given integral is type 1 of the improper integral. Here integral 1 to infinite 1 upon x square dx, then upper limit which is infinite, which is replaced as a t, then applying the limit t as a infinite, integral 1 to t 1 upon x square dx. You all know about the integral of 1 upon x square, that is exactly minus 1 upon x, where x varies from 1 to t. Then substituting the limits, then upper limit minus lower limit, then limit t tends to infinite, minus 1 upon t plus 1. Now t as a infinite, then 1 upon infinite, that is 0. Then our answer which is 1, which is finite. Then our if our limit is exists, then given integral is convergent, and whatever the answer of the integral, that is values of its improper integral. Let's see one more example. Integral minus infinite to 1 x e raised to 2x dx. Here x into e raised to 2x is a continuous everywhere. Here lower limit which is infinite, then given integral is type 1 of improper integral. Integral minus infinite to 1, then minus infinite which is replaced as a t, and limit t tends to minus infinite. Integral t to 1 x e raised to 2x dx. Here integral of uv rule, here x as a consider u and e raised to 2x consider as a v. Then integral of uv rule means limit t tends to infinite, u as it is, integral of v minus derivative of u, integral of v plus and so on. That is a continuous form of the integrating by parts method. Then x as it is, integral of e raised to 2x, that is e raised to 2x by 2, minus derivative of x, that is 1, integral of that term, that is e raised to 2x by 4. Now in derivative of this term, that is 1, that is 0, then 0 into anything 0. Now where x which varies from t to 1, then limit t tends to minus infinite, x e raised to 2x by 2 minus e raised to 2x by 4. Then applying the limits, then limit t tends to minus infinite, x replaced as a 1, then e square by 2 minus e square by 4, minus x replaced as a t, then t e raised to 2t by 2 minus plus e raised to 2t by 4. Now applying the t as a minus infinite, then and simplified this term. First is simplified this term, that will give you limit t tends to minus infinite, e square by 4 minus t is e raised to 2t by 2 plus e raised to 2t by 4, and applying the t as a minus infinite, that will give you e square by 4. That is exactly finite answer. Here you all are about the values of e, that is 2.718, which is finite value. Then given integral which is convergent, because answer which is finite and its value is e square by 4. Now let's see one more example. Discuss the convergence of the integral minus infinite to infinite 1 upon 1 plus x square dx. Here lower limit which is infinite and upper limit which is also infinite, then both the limits are infinite, that is also type 1 of improper integral. Then here firstly we have to consider any real number. Here we consider the 0, means breaking the limit at 0 position, means our integral becomes minus infinite to 0 1 upon 1 plus x square dx plus 0 to infinite 1 upon 1 plus x square dx. Now evaluating the both the integrals separately. Firstly we have to consider the second part, then after we solve the first part, and finally adding that both the integral if both has a conversion and both has a finite value. Let's see for the second integral 0 to infinite 1 upon 1 plus x square dx. Here upper limit which is infinite, then limit t tends to infinite 0 to t 1 upon x 1 plus x square dx. Now integral of that term, that is tan inverse x, where x is varies from 0 to t, then upper limit minus lower limit, then limit t tends to infinite tan inverse t minus tan inverse 0. You all are aware about the values of tan inverse 0, that is 0, then limit t tends to infinite tan inverse t, then t as a infinite, that is tan inverse infinite, that is pi by 2, which is finite value. Our second integral which is finite value. Now we discussed the first integral, that is integral minus infinite to 1 upon 1 plus x square dx. Here lower limit which is infinite, which is replaced as a real number, that is t, then limit t tends to minus infinite integral t to 0 1 upon 1 plus x square dx. Now 1 upon 1 plus x square dx of integral, that is tan inverse x, where x is varies from 1t to 0, then upper limit minus lower limit, then limit t tends to minus infinite tan inverse 0 minus tan inverse t. You all are aware about the values of tan inverse 0, that is 0, then limit t tends to minus infinite minus tan inverse t. Here applying the limit, then it becomes minus of minus tan inverse minus infinite, then values of tan inverse minus infinite, that is minus pi by 2, then minus minus, that is plus, that is exactly pi by 2. That is the answer of second integral. Since both the integrals are convergent, because both the has a finite value which is pi by 2, then the given integral is convergent, and its value which is addition of the two integral, means minus infinite to infinite 1 upon 1 plus x square dx equal to pi by 2 plus pi by 2, that is pi. Let's see one more topic which is improper integral of type 2. It is definite integral in which integral become infinite at one or more points within or at endpoints of the interval of the integration. That means, for example, 0 to 1 1 upon x dx. Here whenever we substitute the upper limit as a x, then it is finite, but 0 replaces as a x, then 1 upon 0, that is infinite. Means whenever we substituting the limits of endpoints, then our integral becomes infinite. Similarly, in second case, integral has a minus 2 to 2 1 upon x square plus 1, then endpoints, whenever we substituting the endpoints, our integral becomes finite, but inside the points of interval, means whenever we substitute x as a 1, then our integral become the infinite. At that case, these are all are the integral has a type 2, improper integral of the type 2. Now for that we have the basically three cases. If our f of x is a continuous on close interval a to open interval b and is discontinuous at b, then integral a to b f of x dx, limit t tends to minus b, integral a to b f of x dx. Since suppose we have the limit a to b, means a position will be considered inside the limit, but at b position our function will be discontinuous. Then we have the total two conditions. Here that one is a negative part, that one is a positive part. Mean this one is a b minus position and this one is a b plus position. Then after that our function becomes discontinuous, and up to inside this our function becomes continuous. Then we consider as a b minus position. Here no need to write the b minus position. You can also simply written as a limit t tends to b integral a to t f of x dx, as you like. Similarly, we discuss the second case, that is if f of x is a continuous on open interval a to close interval b and is discontinuous at a, then integral a to b f of x dx equal to limit t tends to a plus integral t to b f of x dx. Here similarly we have the limit a to b, then position of a means after that is positive and before that is negative point. Means whenever we consider a to b, then here our a plus position, here our a minus position, that our interval a to b means limit t tends to a plus t to be f of x dx. Here, provided that limit, if it is exists, then answer will be finite number, and our improper integral a to b f of x dx is called the convergent if corresponding limit is exists or it is finite answer. If our limit which is infinite or limit does not exist, then it is divergent. Now let's see case 3. If f of x has a discontinuous at c where a less than c less than b, if both the integral a to c f of x dx and c to b f of x dx are convergent, then our integral a to b f of x dx, which is written in form of integral a to c f of x dx plus c to b f of x dx, if both the integrals are convergent, then total integral a to b f of x dx are convergent. If one of them that is divergent, then no need to find the second one, it is automatically divergent. Let's see one more example. Evaluate the integral 0 to 3 1 upon square root of 9 minus x square dx. Here, substituting the upper limit and lower limit in this integral, then whenever we substitute the 0, then it is finite, but whenever we substitute in the 3, then our function becomes infinite. Means that is the improper integral of type 2, and the integral is unbounded at x equal to 3 because our function becomes infinite. Then integral 0 to 3 1 upon square root of 9 minus x square dx equal to limit t tends to 3. Here no need to write 3 or 3 minus, you can write 3 as well as 3 minus as you like. Then here 3 which is replaced as a t, then limit t tends to 3 minus integral 0 to t 1 upon square root of 9 minus x square dx. You all are aware about the formula of integral 1 upon a square minus x square, that is sin inverse x by a, then applying the upper limit minus lower limit, then limit t tends to 3 sin inverse t by 3 minus sin inverse 0. You all are aware about the values of sin inverse 0, that is 0, then substituting the t as a 3, then 3 which is cancel out, then sin inverse 1, that is pi by 2, which is finite answer. If our answer which is finite, then given improper integral is convergent and its value which is pi by 2. Let's see, check out the one more example. Find the values of integral 2 to 3 1 upon square root of 3 minus x dx. Here whenever we substituting the lower limit, then our function becomes finite, but whenever we substitute the upper limit, our function becomes infinite. Then given improper integral is a type 2, then our function is a discontinuous at x equal to 3, means our function is unbounded at x equal to 3. Here which is 3 which is replaced as a t, then our integral becomes limit t tends to 3 minus 2 to t 1 upon square root of 3 minus x dx. Here we can written 3 minus or simply 3 as you like. Now integral of this term, that is we can written as a 3 minus x raised to minus 1 half, then integral of this term, that is minus 2 square root of 3 minus x, where x which is running from 2 to t, then upper limit minus lower limit, then limit t tends to minus 3, x replaced as a t, that means minus 2 square root of 3 minus t plus 2. Now t replaced as a 3 because applying the limit, then first term becomes the 0, then 0 plus 2, that is 2, which is finite answer. If our answer which is finite, then given integral is a convergent, and integral 2 to 3 1 upon square root of 3 minus x dx is equal to 2, that is the values of improper integral. Let's see, check out the more example. Test the convergence integral pi by 2 to pi sec x dx. Firstly, given improper integral which is type 2, and our function f of x is a discontinuous at x equal to pi by 2, means our function which is unbounded at x equal to pi by 2. For that, integral pi by 2 to pi sec x dx, here pi by 2 which is replaced as a t, and applying the limit t tends to pi by 2 plus, here we can written as a simply pi by 2 or pi by 2 plus as you like, then integral t to pi sec x dx. You all are aware about the integral of sec x, that is ln mod of sec x plus tan x, where x which is running from t to pi. Now applying the limits means upper limit minus lower limit. The limit t tends to pi by 2 plus inside the bracket upper limit minus lower limit, then sec pi that is minus 1, 10 pi that is 0. Then in mode of minus 1 that is becomes 1, that is ln 1, that is our answer of upper limit, minus x which is replaced as a t, then minus ln sec t plus 10t in mode. Now t replaced as a pi by 2, that means ln 1 that is 0 minus ln sec pi by 2 that is 0 and 10 pi by 2 that is infinite. Here minus sign which is, then it is becomes minus infinite. Since our limit which is minus infinite or limit does not exist, hence given integral is divergent. If you like this, then thumbs up. If you think that this video will help some of your friends, then do the share with them. If you want to watch more tutorial like this, then you can subscribe my YouTube channel, and whenever I upload the new video, you get the notification. If you have any query regarding this, then feel free contact me. Thank you so much for watching me.